Alright, welcome to the first Muddiest Points Mini-Lecture of 2014. I'll be talking about calculating and comparing performance. First off, I got a lot of really excellent questions. Thank you all for answering. But I got a few that were off topic, but I thought were good and I wanted to address them really quickly here. The first one was, what are transistors? Now this is a fairly basic question, but it's also really interesting. So what I'd like you to do is to read the Wikipedia article on transistors. That'll tell you how transistors work and what they're used for and things like that. Lots of really good information. And also read the CMOS article on Wikipedia, because it tells you how transistors are used to build up into logic gates, which we then use to design processors and execute other functions and things like that. How are all the transistors in the CPUs get smaller? How do we make these things smaller? The big article on this that I'd like you to read to answer this question is the semiconductor fabrication article, because this talks about the process that these companies use to make semiconductors. And the main process that they use to shrink these things is photolithography, where basically you project a pattern, which is the pattern of transistors, onto the silicon, and and we coat the silicon with a chemical that's reactive to light of a certain frequency. So when light hits it, it reacts and basically becomes acid resistant. When it's not hit, when we wash it with acid, whatever is not hit by the light gets washed away, and whatever was hit by the light we keep. So just by changing the light pattern, just by changing the projection, we can make these things smaller. And the article at Intel, the newsroom press release at Intel, is a great, excellent explanation of each of the steps in the semiconductor manufacturing process. And again, the links for all of these are going to be in the video description. What is the difference between the Intel CPUs? We saw a lot of these things. We saw a lot of die pictures of the CPUs, and Wikipedia has an excellent list of the Intel microprocessors and all the things that are different between them, and a lot of great information, so check that out there. Also, I had a question about the conversion of frequencies from megahertz to gigahertz, and the big deal here is the prefix. What does mega mean? What does giga mean? Mega, if we look at the table here, means 1,000 squared, or 10 to the 6th. Giga means 1,000 cubed, or 10 to the 9th. So the difference between these is a factor of 1,000, or 1 order of magnitude. So being able to convert and know the powers associated with giga, mega, kilo, milli, micro, nano, pico, so on and so forth, is going to serve you well. So check out the SI and metric prefixes article on Wikipedia for more information about that. How does adding multiple cores reduce the heat issue? Won't more cores with equal transistors create as much heat as one big one with the same amount? Now this is a really interesting question, so I want to take a little time to answer that. What it comes down to is that not only are we adding cores, but we're also shrinking transistors. So what that means is that it's also about the heat generated per unit area. So the thing is that transistors generate heat when current flows in and out of them when they switch. Here I've set up a little simulation where we can see two transistors switching back and forth, and you can see what I've got it set to is that the devices in the simulation turn red when they're dissipating heat, or when they're using power. And you can see the transistors don't use a lot of power when the current is flowing through them, only when current is flowing into the gate or when it's switching. Right? So it uses the most heat when it transitions from on to off or off to on. So that means that when we increase the clock speed, which is the metric for how often we switch transistors, they generate more heat. We also know that the smaller transistor is, the less the physical size, less electrons it needs to transition from one to another, which means less current, which means less heat generated. Now these two things play together to make it really challenging for us. So let's look at an example. Say we can cool 1 watt per square centimeter per second. So we can take 1 watt of heat of excess heat out of a piece of silicon per square centimeter per second. Now we design a processor to meet this requirement. So we have a processor using a 100 nanometer process that generates 1 watt per square meter at 1 gigahertz. Then we shrink the transistors using a 50 nanometer process. The processor now uses half of the power, half a watt, and is half the size. Now, have we decreased the overall heat output in terms of the rate of heat generated? No, we haven't, because if we take half a watt and divide it by half a centimeter squared, we're still generating 1 watt per square centimeter, which is all that we can take out of it. That means we can't increase the clock rate, we can't double the clock rate, because we can't get the heat out of it fast enough. But we can, because it is smaller, we can put 2 of them in 1 centimeter squared and do twice the work. So we're generating the same heat per unit area, but we're doing twice the work. And this is why we can't increase the clock rate anymore. We can only increase the number of cores and how we build the architectures. Next question, what is the difference between RAM, memory, and register files? And really there's not much structurally. They're very similar in terms of how they're implemented, but how we use them is different. So we'll talk about this a lot more later on in the semester and talk about how these things work and how they interplay. I also got a request for the code for my cat game. You can find it at GitHub at armyouth01/bubblecats, and again there will be a link in the description. I also got some weird questions. The first one was, maybe your dog, was it clean? I'm not sure what that means really. Modern art, which I think is in reference to the CPU dies, but I'm totally not sure. And how does a flux capacitor work? And really, your guess is as good as mine, because looking at this, it doesn't make a whole lot of sense to me. So this guy was a genius. Then the troll face, do we need to know the formula? Answer, yes. Now on to the real questions. The first one was about clock cycle time versus clock speed. I'll talk about architecture versus organization, MIPS versus CPU time, and the relationships between all these variables and how we calculate CPU time, and when to use which equations for CPU time, which means I'm going to be going over a few examples. The first one was clock cycle time, which is period, versus clock speed, which is frequency. And really what we're talking about here when we talk about clocks is any repeating periodic signal that we use in computers to coordinate activity. So here a clock signal is usually represented as a square wave, where we have a falling edge transition, a rising edge transition, and then another falling edge transition, where we go from low to high and then back to low. One set of transitions from low to high and then back to low again is considered one cycle. So when the period that it takes, the time that it takes to go through one cycle is 1 second, that means that we have 1 cycle per second. So that's a measure of frequency. A cycle per second is 1 hertz. So the period of 1 second is frequency of 1 hertz. If we double that frequency, we are cramming more cycles per second. So that means the period has to take half as long. It takes half a second to do 1 cycle. So we can fit 2 cycles in 1 second. That gives us a period of half a second and 2 hertz. If we double it again, that means that the period is halved again. So we go from a half to a quarter, and the frequency is doubled, going up to 4 hertz. So here we've got 4 cycles, 1 cycle, 2 cycles, 3 cycles, 4 cycles in 1 second, which gives us a period of a quarter of a second and 4 hertz. The things that you need to remember, and sort of just by rote memory, is that clock cycle time is the same thing as period, and it's represented using a T in our equations. Clock cycle rate is the same thing as clock speed, is the same thing as frequency, and we use it as F in our equations. So the relationship between these two variables is that frequency is equal to 1 over period. Next is architecture versus organization, and I need to get back to a couple of definitions here. When I talk about architecture, I'm talking about the interface standard, basically the language that the machine understands, known as the instruction set architecture. So when we say I have an x86 which is either made by Intel or by AMD, the x86 is the instruction set architecture. It's the same language, which means that they can both run Windows natively, so they're speaking the same language, but the underlying architecture, the underlying organization is different. The organization is how the architecture is implemented in hardware, and this can be drastically different between designs. So for example, say I've got 2 ARM processors. They have the same add instruction, same encoding. 2 programs can run the exact same on the 2 processors, except they might have different performance characteristics. For example, the hardware that implements the add instruction might be very different. For instance, we've got a ripple carry adder over here, which is slow and cheap. It takes for maybe 100 nanoseconds to execute the add operation because we don't use a lot of hardware and the signal has to propagate through all of these gates here. So this is cheap but slow. On the other hand, we've got a large, expensive, and fast implementation. This is a carry look-ahead adder. It performs exactly the same operation as the ripple carry adder, but it uses a lot more hardware, you can see here. So this would be a lot faster, but a lot more expensive. The two trade-offs are how we organize our processors. So the organization is the implementation of the architecture. The architecture is the standard for talking to it. Basically, architecture is the machine language or the instruction set that the machine uses. MIPS versus CPU time. The thing to remember here is that the CPU time and speed is our measure of performance. It's how long it takes to execute a standard program, and it's a good measurement because time is something we can all agree on. It's a good metric for performance. We care about time the most. MIPS is defined as millions of instructions per second, and it's a measure of throughput. It doesn't account for program length or how complex instructions are. Example, say I've got an ARM processor that has hundreds of different instructions that it can execute. That means it's got an instruction specialized for adding, it's got an instruction specialized for jumping, things like that, which makes it much more efficient than a monoprocessor or a single instruction processor. These things exist. Go look it up on Wikipedia. Totally crazy. So basically, if I wanted to do a add instruction on MIPS, I could use one instruction per add, but because the hardware is bigger, it takes 15 million instructions per second to run a given program. Whereas a monoprocessor might do 1,000 MIPS because it only executes one instruction. The hardware is super simple. We can crank it as fast as we can, but it might take 50 instructions to do an add. So given the same program and different architectures and necessarily different compilers, the ARM processor, even though it looks like it should be faster because it's in MIPS, can execute quicker because it's got all this specialized hardware, whereas the monoprocessor might take 50 milliseconds to execute the program, making it much slower. So really the performance metric of time, of execution time and speed, is much more relevant than throughput because we care about different types of processors and how they react to different types of programs. What's the relationship between CPI, IC, CPU time, etc.? So this is the big beefy part. So let's go back to some definitions. The CPU time, what we represent as E, is how long it takes to execute a given program on a given machine. The clock rate and clock rate, which is a frequency, and clock cycle time, which is a period, we just talked about and how they're related. And we've got the number of cycles, C, which is the number of clock cycles in a given program. And this is kind of mysterious because we don't deal with this a whole lot, but we'll get to how it works. Just take it as given for now. We've also got the instruction count, which is the number of instructions in a given program. We've got the cycles per instruction, which is the average number of cycles per instruction, and this is dependent on the organization. Now, the most basic part is that the execution time of a program is the number of cycles that it takes to execute that program times how long it takes to execute one cycle. That's pretty straightforward. Number of cycles times time to execute one cycle is the total execution time. Also, we've got the execution time is equal to the number of cycles to finish a program divided by the frequency or speed of cycles as they go by. So given a program, how do we calculate C? If we don't know C, we can either infer it from these two, or we might need to know how many instructions there are first off. Now the problem is that not all instructions take the same time to execute. For example, a multiply instruction might take 5 cycles and an add instruction might take 2. So we take them in aggregate and use the average cycles per instruction, or CPI. So if we know the average number of cycles per instruction and we know the number of instructions, then we just multiply those two together to get the total number of cycles that it takes to execute a program. Then we substitute that into our execution time equations, and we get these two guys, which are pretty straightforward, right? So the number of instructions times the cycles per instruction gives us the total number of cycles times how long it takes to execute one cycle gives us the total execution time, and the related equation for using frequency instead. So, say we don't have CPI, we can calculate it from our instruction mix. So usually what will happen here is we'll give you a bunch of instruction types, and each one will have an associated CPI for that instruction type. So this says that instructions of type A take 1 cycle, instructions of type B take 2 cycles, instructions of type C takes 3 cycles. Then we give you a listing of the number of instructions of each type by a certain program. So program 1 has 6 instructions of type A, which take CPI of 1, 2 instructions of type B, which take CPI of 2, 1 instruction of type C, which takes CPI of 3. Now, to calculate the overall CPI of the program, we take the CPI of the instruction and then multiply it by the share of the program that it takes. So IC is the total instruction count, so across the whole program. So we add all of these together, you get 9 from 6, 2, and 1. So there'll be a 9 here, and then we take the individual instruction cycle count, which is 6, so 6 over 9 times CPI of A, which is 1, so that'll give us 6 over 9, or 2/3. We do the same thing for these, so that'll be instruction count of B, which is 2, divided by 9 times 2, then instruction count of C, which is 1, times 3, which is CPI of C, divided by 9, gives us 3/9, or 1/9, or 1/3, sorry. Sometimes we'll also give you a instruction mix like this, where the instruction count is implied or not given. In this case, you just take the percentage, multiply it by the CPI, and then add those up together. So here we've given you the types, the share built in. And you can kind of see where that comes from, because each one of these is a percentage. We're taking the instruction count of type B and dividing it by the total instruction count, which gives us the percent of that particular instruction, how that particular instruction affects the overall program. So now it comes back to when to use what equation. It always comes back to the execution time. So if you're given a total number of cycles and cycle time or frequency, we can calculate the execution time directly, or any of the variables that are missing. If you're given IC and CPI of the overall program, then we calculate C by multiplying the instruction count by the CPI of the overall program, then plug and chug. If you're given a table of instruction CPIs and mixes, then you use either, if you're given instruction counts by instruction type or percentages by instruction type, use these two equations. So let's look at a couple of examples. The first example, the benchmark program takes 500 cycles to execute. Computer A has a clock rate of 50 megahertz and computer B has a clock rate of 25 megahertz. Which is faster and by how much? In this problem, we had a C, or number of cycles, in the program equal to 500. The frequency of processor A is 50 megahertz. The frequency of processor B is 25 megahertz. And we can basically just plug and chug to find out our execution time. So execution time of A is equal to the number of cycles divided by the frequency of A, which is 500 over 50 times megahertz is 10 to the 6th. The 50 cancels out, so we get a 10 from that, which gives us 10 times 10 to the 6th, 10 to the negative 6, because the 6 is on the bottom, which is equal to 10 microseconds. E of B is equal to C over F of B, which is, in this case, 500 divided by 25 times 10 to the 6th, which is equal to, in this case, 20 times 10 to the negative 6th, which is 20 microseconds. To find out which one is faster, we do, we take our n equation, we want to say, in this case, this one is less, so this is the longer one. We want to say A is faster than B by a certain amount, and since these are execution times, we put E of B on top and E of A on the bottom, which gives us a 20 microseconds over 10 microseconds. So we can say that B is 2 times faster than A. Then in example 2, a computer has a clock period of 500 nanoseconds. A compiler translates a program into instructions that take 150 cycles, and compiler B translates the same program into instructions that take 125 cycles. Which compiler is faster, and by how much? For example 2, we're given the clock period, which in this case, T is equal to 500 nanoseconds, and a nanosecond is a billionth of a second, so that's 500 times 10 to the negative 9. We're also given the clock cycles of program A, which is 150, and we're given the clock cycles of program B, which is 125. Now again, to calculate the execution time, we just plug these in. In this case, it's C of A times T, which is 150 times 500 times 10 to the negative 9, which is, in this case, 75,000 times 10 to the negative 9. We take these zeros and hop them back, which decreases this to 75 times 10 to the negative 6, which is 75 microseconds. Then E of B is C of B times T, which is 125 times 500 times 10 to the negative 9, which is 62,500 times 10 to the negative 9, which is 62.5 times 10 to the negative 6, or 62.5 microseconds. Right out to the edge of the thing there, right? Which one's faster? This one is smaller, so the execution time is lower there, so we put A on top in this time, so N is equal to E of A over E of B, which is 75 over 62.5, which is 1.2. So we can say that B is 1.2 times faster than A. In example 3, a program consists of 150 instructions. The program is executed on 2 different processors with the same architecture. Processor A has an overall CPI of 1.5 and a clock rate of 6 MHz. Processor B has an overall CPI of 2.5 and a clock rate of 12 MHz. Which is faster? In example 3, we're given the instruction count of the program is equal to 150. The CPI of A is equal to 1.5, right? And also the frequency of A is equal to 6 megahertz, which is 10 to the 6th. Then we're also given CPI of B is equal to 2.5, and the frequency of B is equal to 12 megahertz. Now, since we're given IC and CPI, we're going to use, instead of the CA equation, we're going to use the IC times CPI divided by F of A equation to determine E of A. So that's IC times CPI divided by frequency of A, so that's the CPI of A, which gives us 150 times 1.5 over 6 times 10 to the 6th, which spits out 37.5 microseconds. And then E of B is equal to IC times CPI of B over F of B is equal to 150 times 2.5 over 12 times 10 to the 6th, which is equal to 31.25 microseconds. And in this case, because the execution time of B is lower, B is faster. And if we go through the calculation, you'll find that B is 1.2 times faster than A. And finally, you're given 3 different compilers that generate programs with different instruction mixes. They all have the same number of instructions and are executed on the same machine. Which program is faster? And you can see we give you % instruction mixes. In example 4, we're given 3 different programs generated by different compilers with different instruction mixes. They end up all having the same number of instructions, and they're all executed on the same machine, which means that IC is the same and frequency is the same. So our task is to determine which program is faster. Because those things are the same, we don't have to go all the way through the execution time calculation. The only thing that's changing, because we're given these mixes, is our overall CPI. So let's calculate the CPI of A. That's going to be that long equation. In this case, we're given percentages, so we're going to take the percentage of the type A instructions times the CPI of that type. So in this case, it's the CPI is 9 times 0.3, and then we're going to add up each of the different types multiplied by their respective CPIs. So the next one is 7 times 0.2 plus 3 times 0.5. And that gives us a total of 5.6 for CPI of A. Do the same thing for CPI of B. So that's 9 times 0.4 plus 7 times 0.3 plus 3 times 0.3 is equal to 6.6. Then CPI of C is, actually these are different programs, not A, B, and C, but 1, 2, and 3 for the different programs there. Then it's 9 times 0.45 plus 7 times 0.1 plus 3 times 0.45 is equal to 6.1. Which one is fastest? In this case, we're looking for low CPIs. The lower the clocks per instruction or cycles per instruction, the better, because we're able to do more instructions with less cycles, right? So we're looking for the lowest value, which is CPI of 1. Program 1 wins, is the fastest in this case. Okay, now that we've looked at all those examples, we can answer which is better, higher or lower. We're looking for higher speeds and higher clock rates, right? So always shoot for the better speed as higher speeds and better clock rate as higher clock rates. We want to lower execution time, we want to lower clocks per instruction, and we want to lower instruction count. So when these are lower, we get higher performance. When these are higher, we get higher performance. Okay? So that's it. Let me know if you have any questions, and I'll see you guys in class.